Our everyday world feels solid and predictable. We expect objects to have definite properties whether we look at them or not. But dive into the quantum realm, the world of atoms and particles, and things get bizarre. Quantum mechanics, the physics of the very small, constantly challenges our intuition. It suggests reality isn't quite what it seems. One particular type of experiment has repeatedly delivered results that defy classical logic and even shock the scientists performing them. Imagine sending tiny particles, like electrons or photons, towards a barrier with two narrow openings. Behind the barrier is a screen to record where each particle hits. Classically, you'd expect two distinct bands of hits, one aligned with each slit, as if the particles simply went through one hole or the other. However, when you fire these quantum particles one at a time, they don't create two bands. Instead, they build up an interference pattern on the screen, a series of bright and dark bands. This pattern is what you'd expect if waves, not particles, were passing through both slits simultaneously and interfering with themselves. This wave-like behavior for single particles is already strange. But the experiment gets even weirder. What happens if you try to figure out which slit the particle actually went through? If you place a detector at the slits to observe its path, the interference pattern vanishes. The particles suddenly behave like classical particles again, creating just two bands on the screen. Simply by observing or measuring which path the particle took, you change its behavior from wave-like to particle-like. It's as if the particle knows it's being watched. This result is profoundly unsettling. It suggests that a particle doesn't have a definite path until it's measured. Its state seems to exist as a superposition of possibilities until observation forces it to choose one reality. This challenges our fundamental ideas about objective reality and cause and effect. Does reality exist independently of whether we observe it? Do our measurements somehow influence the past or the present state of a particle in ways that defy common sense? These experiments continue to push the boundaries of our understanding.